Having talked about electrolytes, it's time to move on to acid-base balance because electrolytes have a huge impact on acid-base balance. So think back, maybe by 156. Look in the upper right. See there are three enzymes there, the red one, the blue one, the green one. And then look on the bottom. See how there's a scale of pH going from 3 up to 12? Remember pH 3, that'd be very acidic. pH 12, very alkaline, very basic. So notice that the red enzyme only works from pH like 3 to 6. Can you think of an enzyme that we've seen that would be like that? Maybe lingual lipase, secreted in the mouth but doesn't work until it hits the highly acidic environment of the stomach. Well, look at like the green enzyme. Green enzyme only works between like 6.5 and 12. That would probably be like a lot of the pancreatic digestive enzymes. They need the relatively alkaline environment of the duodenum in order to work. The problem is that if you screw up your acid-base balance, one of the things that happens is certain enzymes are going to stop working. And when that happens, you're in big damn trouble, okay? So an important part of homeostasis, metabolism depends on enzymes. Enzymes are highly pH sensitive. They're also sensitive to temperature and other things, but pH is one thing they're very sensitive to. Normal range of pH, you should know this inside out, 7.35 to 7.45. That's of all your ECF, in particular the blood, all right? It varies from place to place. I remember the blood leaving the stomach, there was the alkaline tide. So yeah, here and there it's going to vary, but overall that's what it should be. Remember, your blood is constantly intermixing, going everywhere in your body within 1 minute. So challenges to acid-base balance. Lots of things can screw up your acid-base balance. Lactic acids. So remember, lactic acid is a byproduct of anaerobic fermentation. Now, it's hard to exercise enough to cause an actual problem with lactic acid, but there are various conditions under which lactic acids can build up and cause problems. Phosphoric acids, fatty acids, ketones, and carbonic acids, all of these things have an impact on pH, and therefore we have to have some way of coping with that high variation in our internal physiological environment. Let's go back and remember stuff about acids and bases from some previous biology class. So acids, all right, strong acids ionize freely, markedly lower pH. Weak acids ionize only slightly. So look in the bottom left. You see hydrochloric acid. When hydrochloric acid in water, don't add, do as your order, add acid to water, right? Is that one? The same goes. Red on yellow, kill a fellow. We've got red hydrogens, and chlorides, and acid. Red acid on fellows to kill. No, all right. So notice on the left, HCl, when you put in aqueous solution, it completely dissociates. The hydrogens completely break free of the chlorides. Look on the right, though, we've got acetic acid, vinegar. Notice in solution, some dissociate, some don't. That's more typical of weak acids. That property and buffers then end up being weak acids and weak bases. The reason those work really well as buffers is because they can either grab or let go of hydrogens in response to their current acid-base environment. So bases, strong bases, same deal, just like the acids, and same strong, weak, the degree of dissociation happens in both. So a nice chart there up in the top. It might be interesting to go through. It's a European chart, it looks like. Buffers here. So these are things that resist a change in pH, all right? So can convert strong acids or bases to weak ones, all right? So physiological buffers, these are systems that control output of acids, bases, or carbon dioxide, and we know those already. We've seen them. So the urinary system buffers the greatest quantity, has the biggest effect on your acid-base balance, but it takes hours or even days. So it's powerful, but it's slow. Respiratory system buffers within minutes. It's very, very fast, relatively speaking, compared to the urinary, but it's not nearly as powerful. All right, so keep that in mind because we're going to see that later in terms of clinical applications. All right, whether urinary can make up for a respiratory problem, whether respiratory can make up for a urinary problem. Maybe one can, maybe the other one can't, because of the power of the system. Then there are three chemical buffer systems, and we've actually talked about these. Now, these restore pH in fractions of a second, okay? So bicarbonate, phosphate, and protein systems bind hydrogens All of them do. So bicarbonate is out there in the ECF. Phosphate and proteins are in the ICF. What they're constantly doing is grabbing or letting go of hydrogens, and that way they're controlling the acid-base balance. If there are too many, then they soak them up. If there's not enough, then they let them go. They respond naturally that way. It's the characteristic of the molecule. So they are buffers, just like Bruce in the upper right and Michael in the lower right, who, I don't know, never mind. Okay, so 5 buffer systems. Remember, 3 chemical, 2 physiological, 5 buffering systems. I might ask you about that at some point. The 5 buffering systems. So bicarbonate, we've been over and over this when we did the respiratory system. So we already know how all of this works, okay? When you mix water and carbon dioxide, you don't even have no chemistry, just count the damn letters. You end up with 2 H's, 1 C, and 3 O's. That's carbonic acid. And as a weak acid, well, as an acid, it will dissociate to some degree. It's a weak acid, so it partially dissociates. That's why it works well as a buffer. So you see on the far right of that equation then, it can let go of a hydrogen, and then the bicarbonate ion is the conjugate base. So when we drive the reaction to the right, we are releasing hydrogen, so we're making things more acidic, okay? When we drive the reaction to the left, we're getting rid of hydrogens, right? Therefore, we're making it less acidic or more alkaline, okay? So urinary and respiratory, as we just mentioned before, work together, all right? So you can raise and lower pH using both. Use your lungs, use your kidneys. How does that work? Well, the lungs, you're either holding CO2 in or blowing CO2 out. With the kidneys, what were we doing again? You should stop the video and can you think? How did the kidneys control your acid base? Yeah, by moving things between the blood and the urine, all right? So, and then also then controlling the excretion in the tubules of both hydrogens or of bicarbonates. So the kidney is capable of secreting or retaining in the nephron tubules either hydrogens or bicarbonates, and that's how it controls it. Remember, the kidney is much more powerful, but it takes longer to do that. Respiratory is quick, but it's not very powerful. So to lower pH, the kidneys excrete bicarb. To raise pH, kidneys excrete hydrogen, and the lungs excrete CO2. All right? That's the bicarbonate. That's the buffer system of the ECF. Now let's look at one of the buffer systems of the ICF. That's the phosphate buffer system. So once again, it's the same reaction that we saw before with bicarbonate, except now it's phosphorus instead. But the same principle still holds true. When the reaction goes to the right, you're creating lots of free hydrogen, so you're becoming more acidic. When the equation goes to the left, you're picking up hydrogens, and so you become more alkaline. So reactions proceed to the right, release hydrogen, lower pH. Reactions proceed to the left, raise pH, okay? Important in the ICF and the renal tubules, all right? So remember, you should think right now, what ion goes with phosphate? What ion, in terms of renal excretion and reabsorption, what ion is paired with phosphate? In the same way that sodium and potassium are paired. Who is paired with phosphate? Yeah, calcium. So think about that, all right? Where phosphates are more concentrated, function closer to their optimal pH of 6.8. So the kidney, again, in the tubules, is controlling either withholding or secreting phosphate. Constant production of metabolic acids creates pH values from 4.5 to 7.4 in the ICF, average around 7.0. So notice ICF is different than ECF. Remember, what's the pH of ECF? 7.35 to 7.45. ICF varies considerably more, averages around 7.0, and that's because of all the metabolic processes going on inside the cells. That's why before, when I asked that question, what was lymph most similar to, and some of you said intracellular fluid. No, intracellular fluid is vastly different than any ECF, okay? So make sure, let's get that straight. And you know the occupation of the guy in the lower left? That's a soda jerk. And when I was a kid, they had that occupation. And you would go down to the soda fountain, and if you wanted a Coca-Cola, you know what they did? They didn't have it already made. They would have to make it for you. They would take a bottle of Coke syrup and spoon one into the glass, and then they would fill it with phosphate. And if you look now in most sodas, they're very high in phosphate or phosphoric acid, all right? That says supposed to give it a sparkly, bubbly flavor or something. And then in the lower right, cherry phosphate, that was a favorite drink. You go down to the soda fountain, and 15 cents, they put in some cherry syrup and then fill that thing up with phosphate seltzer. Oh man, was that good. So finally, the fifth now. So we've had 5 buffering systems, do you remember? Do you remember what they are? 2 of them were organ systems, 3 of them were chemical buffers. What were the organ systems? Urinary, respiratory. What are the 3 chemical buffers? We already talked about 2. The bicarbonate and the phosphate. Now we're on the 3rd one. This is also like the phosphate. This is intracellular. So we're looking at a protein buffering system. And how the hell does this work? Wait, proteins. What? Proteins. Oh my God. Yeah, remember, proteins are the workers of your body. They're carrying, wearing hard hats, carrying lunch pails, punching a time clock, all right? So remember, proteins are made of amino acids, right? You knew that. Protein is a big string of beads. Each bead is an amino acid. Remember the structure of an amino acid. Look down at the bottom left. So they're showing it in its hydrated form here. So we're talking about the amino group is an NH2 group, and then the carboxylic acid would be a COOH. Here, the hydrogen is now stuck on the amino end. But that's how this works. Proteins can either grab a hydrogen on the amino end, or they let go on the amino end and they grab the hydrogen over on the carboxylic acid end. And that O minus becomes an OH. So see what they're doing? They're either grabbing hydrogens or they're letting go of hydrogens. And that's exactly what a buffer is supposed to do. So these work very well inside the cell, all right? Because remember, proteins can be hundreds of amino acids long. So you've got just tons of these side chains, and therefore the protein buffers easily balance the pH of the ICF. And respiratory control, all right, so once again, we're talking about changing the breathing rate. Test yourself right now. What's the standard breathing rate? You should know, 12 to 20 breaths per minute. So if you breathe less than that, we are hypoventilating. More than that, we are hyperventilating, okay? And that's going to change pH. This is much more powerful than the chemical buffers. So if we were in class, I would draw 2 arrows on the board going opposite directions, and I would show how these things go in terms of strength versus speed. The chemical buffers are the fastest, but they are the very weakest. The respiratory system is in between the other two. It's faster than the chemical buffers, but slower. It's slower than the chemical buffers, but it's faster than the urinary system, all right? And it's also intermediate in terms of power. It's more powerful than the chemical buffers, but not as powerful as urinary. So it works much better than chemicals, not as good as urinary. It collaborates with the bicarbonate system, all right? So again, we're moving those hydrogens along on the bicarb, all right, on the carbon dioxide and water, the carbonic acid, all right? So the top line there, if we're moving the reaction to the right, we're releasing hydrogens, becoming more acidic, lowering the pH. If we're driving that reaction to the left, we're raising pH by grabbing the hydrogens. And that's what the buffering system does in your body. It doesn't need anybody to tell it what to do. If there's way too many hydrogens, it automatically starts grabbing them. And if there's way too few hydrogens, then it automatically starts letting them go. So that's just a property of the molecule. So increased CO2 and lower pH stimulate pulmonary ventilation, while an increase in pH inhibits pulmonary ventilation. So you should be able to figure all that out. If you've got too much CO2 inside of you and your pH therefore is too low, because remember, CO2 works like an acid. I told you, always remember that. Don't ever forget that. CO2 in your body works like acid. CO2 lowers your pH, therefore what do? You need to get rid of it. How do you get rid of it? With respiratory system. Blow the damn stuff out. So yeah, you hyperventilate. Whereas if you hypoventilate, if you hold the CO2 in, that's going to make you more acidic. And an increase in pH inhibits pulmonary ventilation. So pH too high, then you don't want to breathe as fast. Nice chart in the lower left. New beginnings in breathing, a guided meditation. Tell you what, you go and I'll drive you. If you woke up breathing, congratulations, you have another chance, okay? Now, the kidneys, here we are. The most powerful method for controlling pH in the body. Most powerful buffer system, but slow. It's the slowest. Slow, but it's powerful. Slow, but powerful. Just like, never mind. Renal tubules secrete hydrogen in the tubular fluid, then excreted in the urine. If we were in class, I would put this on the board because this is such a wonderful diagram, just like we did with the chloride shift and the picking up of hydrogen and oxygen on the hemoglobin. This is such a great diagram. So look on the far left. This deserves a couple of minutes. So on the far left, we have the fluid in the tubule lumen, all right? In other words, this is going to be urine, but we don't call it urine yet because we're still modifying its structure, its contents. Then we have these cells in the PCT, all right? These are PCT cells. Remember, this is where we do 65% of all of our reabsorption after putting all that stuff into the filtrate. So right now, the fluid in the tubule lumen, the filtrate, has got all the stuff in it that we just dumped out in the glomerulus. Here are the proximal convoluted cells, and now what they're trying to do is get stuff back into the blood because this is good stuff and we need it, okay? So look at what happens here. We've got in the left, we've got a sodium hydrogen pump, all right? Just another pump that's moving sodium where we want it. We can pull it out of the urine and put it back into the cell of the PCT. And then look, who do we use next? Oh my gosh, will you look at that? It's the sodium-potassium pump, damn it. Pumping those sodiums into the blood and pumping the potassiums into the cell of the PCT, which is where potassium is supposed to be. It's the main intracellular cation. And then look at, we can pull CO2 out of the urine and we can pull CO2 out of the blood. And what do we have? We mix them with water inside of the cell and we create carbonic acid. And then what we can do is we can send the hydrogens into the urine and we can send the bicarbs into the blood, where the bicarbs become the main buffer of the blood. Oh my God, isn't that just like poetry in action? Look at that, kids. Oh my God, that's just incredible. Look at what we did. We balanced pH. We put bicarbonate into the bloods where it's now the buffer of the blood. I mean, we put hydrogen into the urine. Remember, average pH of urine was around 6. So that's how we can we can control our acid-base balance by getting rid of hydrogens and also by absorbing bicarbs. Look at how powerful the kidney is. Oh my God, this is just incredible, all right? So make sure you know that. I normally ask questions about this. So, acid-base balance, again, you should know normal. That should be second nature by now, 735 to 745. If you go under 735, you are now in a state of acidosis. And if your pH drops as low as 6.8, we have a special name for you. We call you dead. All right, that's how serious acid-base balance is. And again, going the other direction, 7.45 is normal. If you're above that, you're too basic. We call that alkalosis. And if your pH hits 8, again, you get the special designation. You are dead. Okay, now this is just to try to show, how I remember before I mentioned that the damn potassium imbalances are just, oh my God, they're just a nightmare. But here's an example of how it works and why it's so complicated, because potassium can work in so many ways. So acidosis here, okay? If you have acidosis, you have way too much hydrogen around. It's going to diffuse into the cells, okay? It drives potassium out because they're the same charge. Positive hydrogen entering drives the positive potassium out. So what does that do? It elevates potassium in the ECF. And so what do we have there in that case? We have hyperkalemia. And we can see here also a hydrogen buffer by protein in the ICF causes membrane hyperpolarization. Nerve and muscle cells are hard to stimulate. So remember, it's sodium-potassium pump. We needed those potassium-sodium concentrations. Those determine the action potential. So here's what's happening, therefore. We've seen then, therefore, that acidosis it drives the potassium out. Now we end up with membrane hyperpolarization. Nerve and muscle cells are hard to stimulate. So people are sluggish. They're unresponsive, okay? That's what acidosis does. Think of acidosis as being that way. People on acidosis are just not very active, all right? CNS depression may lead to death. In other words, you can slow the body down so incredibly, so intensely that you just cause it to stop, all right? So just shuts down everything, okay? So that's the diagram on the upper part of the diagram on the left and on the upper part of the diagram on the right. And so now, oh my God, the song is playing right now. I just saw the Chieftains here in concert in Tucson just a little bit when they played this song. So awesome, so amazing. They had like 15 people on the stage all playing. So Alkalosis and hypokalemia. What were we talking about here? Oh yeah, alkalosis and hypokalemia. Okay, right. Okay, so let's figure out what's going on here. Alkalosis, so hydrogens are going to diffuse out of the cells in order to balance out your acid base, and therefore potassium diffuses in, all right? Membranes become depolarized, because remember potassium here, we're talking about action potentials. This is affecting the concentration gradients and the electrical gradients for the action potentials. What happens? Membranes depolarize too quickly, nerves overstimulate muscles. So what do we get now? Spasms, tetany, convulsions, respiratory paralysis. So this is the classic picture of the patient in alkalosis. They are bouncing off the walls. I mean, or not so much just from desire. I mean, they're bouncing off the walls because their muscles are contracting out of control. All right, So I want you to have a clear idea in your head of what a person in severe acidosis looks like versus what a person in severe alkalosis looks like. So I found these two pictures for you. On the lower left, we have the orangutan there saying, oh, what to do, what to do. So it's sluggish, it's not doing much, it's not very active. Put that picture in your head next to acidosis. That's what acidosis looks like, all right? So signs and symptoms: CNS depression. The brain is depressed, it's not sending out as many signals, so the body's not doing as much, okay? Sluggish reflexes, confusion. The brain itself isn't working well. Action potentials are not firing as much as they should. So eventually, coma, eventually death. Whereas, look on the right, okay? How about alkalosis? Remember, that's hyperexcitability of neuromuscular systems. So muscle spasms, muscle tetany, convulsions, eventually paralysis of respiratory muscles, and again, death. But what's that patient going to look like? So here I show a picture from drawn, I think, by an obviously disturbed young child. You're just totally frazzled. Person in alkalosis, hyperexcitability, muscle spasms. They may be talking a mile a minute. They may be blabbering. They're convulsing. Oh my God. So you get the two. Put that picture in your head, okay? And that goes with alkalosis. Like just totally frazzled, your body's contracting, convulsing, everything. Picture on the left, alkalosis. That's the picture on the left, acidosis, the orangutan. Whenever I do this, I think of my son when he was in, I don't know, like third grade. They did this exercise in class, and the teacher said, okay, kids, today we're going to do a different kind of an assignment or class activity. I'm going to show you a picture, and I want you to write a story about the picture. Now, there's no right or wrong. I just want you to use your imagination and write a story that goes with the picture that you see, okay? So she held up a picture that showed a little boy standing in his front yard with a big wooden two-story house behind him. There was a huge tree in the yard, and there were leaves all over the yard, and the boy had a rake. So and there was a little pile of leaves. The boy was raking up the leaves into a pile. So the teacher said, okay, so I want you to write a story about this picture. You just, when there's no right or wrong, your imagination, whatever you want to do. And so most of the kids in class, what it did is it turned out to be a way to get the glass half full and the glass half empty people identified, okay? Because like half the class said, oh, there's this little boy, and he got home and he wanted to go out and play, and his mom said, no, you have to rake the leaves, and so he's pissed off and he's raking the leaves. And the other little boy got home, and fall was his favorite time of year. He was so excited to rake up the leaves and call his friends over. They would jump in the leaf pile. Basically, every kid in the class wrote one of those two stories, except my son. My son's story was, The Boy Who Killed with a Rake. And it was about a little boy who was sad and lonely, and he didn't have any friends, and nobody liked him. And so one day he decided to start killing people with his rake. And he went through the world killing people with his rake, and this made him even sadder and lonelier, because now the only people who could have been his friends were dead because he killed them with the rake. But then one day, while he was out killing people with the rake, he met another little boy who killed with a shovel. And they became good friends, and they went through life together, killing people with their rake and shovel until finally one of them killed the other one. The end. So I got a call from the principal. Said, your son wrote a story that we find a little disturbing. And I said, well, what was the assignment? What's going on? He told me what the assignment was, told me what my kid did. And I said, that's fucking brilliant. Just back off. I mean, oh my God. You said there was no right or wrong. Use your imagination. I mean, look at that. It's got story. It's got dialogue. It's got a plot. I mean, there's development of the story. There's development of the characters. My son, look, he doesn't need a counselor. He needs a literary agent, okay? And just stop talking to him, by the way, okay, will you? So it all worked out okay. Okay, which exerts the most powerful control over pH? Respiratory, urinary, phosphate, bicarb, protein. All right, the 5 buffer systems, there you go. Remember which one's fastest, which one's slowest, which one's most powerful, which one's least powerful. All right, here I'm asking which is powerful, not fast. Urinary. It's also the slowest. Who was the fastest? The 3 chemicals. All right, they were also the weakest. Okay, I'll see you next time. You can see my truck and my tent. This is Whitmore Wash. This is a 50-mile 4-wheel drive road. It's not all that bad until you like the last 7 miles are through this volcanic field. And it's just all this incredibly rough, sharp volcanic rock everywhere. I carry 2 spare tires. I go through here. I've never seen anybody here except once as I was leaving. I saw somebody else on the way in. But you can swim in the Colorado right down where that first sandbar is. There is a trail that actually leads down there. So I took this picture. I'd just come back from a swim in the Colorado. So awesome, just by yourself. Have the whole Grand Canyon to yourself. Not a soul there except you. Awesome.